Swayam Prabha. Digital India. Educated India.
So Rahul is asking, so basically ISA abstracts programs and processor. Processor internals changes don't affect whether the program will execute or not.
Right.
Okay.
That is what I mean. If you are, or in fact, do they have the ability to unmute themselves?
Yeah, actually I prefer because sometimes questions are not clear while reading.
Right, right. So maybe
So
you can.
yeah,
I
Rahul,
will
you
answer.
can please.
I will answer, and the next one, then he can unmute and tell me whether I was able to understand what he said is correct or not.
Okay, okay,
Right.
okay.
So, Rahul, I think you are right in the sense that the ISA is an agreement between the program and the processor, in the sense that the processor gives an assurance to the program that as long as you stick to the instructions which are part of the instruction set and adhere to that operands and other things, I will make sure that that program is that particular instruction is executed and the results are produced, the flags are affected in the way that is expected of me. And uh, that is the assurance that it gives. And given let's say given an ISA, to give an example, x86 is an ISA which Intel also makes and AMD also makes. So a program which was written in 386 maybe 20 years ago, that will run exactly the same way on a today's AMD processor and today's Intel processor. That is the beauty of ISA, that the ISA separates out the microarchitecture from the programs. So microarchitecture is the implementation. How you do it, how much frequency will your microarchitecture run at, how many cycles will instructions take. All this is dependent on the microarchitecture. But two processors having same ISA can have two different microarchitecture. Rahul, does that answer your question? Or you can unmute yourself and seek further clarification.
Yes, sir. And actually, I was having the same doubt that you just cleared, that if the Intel processor is there and if AMD processor is there, so they need to share the same ISA. Like if they don't, then AMD processor won't work uh,
Correct.
over there, right?
Correct.
So yes, I was having this doubt as well. And sir, where does this interface is placed between? Like processor is my hardware, and
Yes.
operating system is my system software
Yes.
basically. So where this interface is located?
Correct. So this is precisely between them, in the sense that you take any program. I mean, let's for the moment take a simple case like an 8085. Okay, that will be easier to understand because there is no operating system there. You simply write a program I mean, for simplicity, let us say you write a program in the assembly language of 8085 to add two numbers, or two numbers are in register, and or rather you read a number from memory, read another number from memory, add the two and store the result back in the memory. You, let's say, write a program having, let's say, 6 or 7 instruction. Then this program is being executed by the processor. So that is the ISA. That is the ISA is between the program and the processor. So the program communicates to the processor what it want, what it should do is that interface. Okay. And
Okay.
to take further that AMD and Intel analogy, what can happen is that there is a base instruction set. Okay, I keep mentioning I32. So that is a base instruction set. However, Intel over a period of time kept adding instructions called as SIMD instructions, SSE, SSE2, because of which I said that a program written for a Pentium 4 may not run on 386 because there are more instructions there. Similarly, AMD can make their own additional instructions which work on them, which may not work on Intel processor. So how is this done? So AutoCAD. So AutoCAD is the same program. How will it run on an Intel processor and how will it run on, let's say, AMD processor? So what they do is they use what are called as libraries. So libraries which are tuned for AMD and libraries which are tuned for Intel. So those nuances which are present on these individual processors, they will be taken care by a specialized set of programs, which will, so they will have a base program which will run on both of them, and they will have an additional program which will be specific to an architecture. Okay.
Okay, sir. And sir, how this ISA is flexible for increasing the efficiency uh, over the increasing efficiency of processor? Like if there is one program A and it is running on 8085, and now the same program we are running on suppose Pentium. So
Yeah.
does that also increases the efficiency of running that program, the speed of that program over processor increasing its capabilities?
Right. So it does. I mean, let's take example of a 486 and a Pentium. Okay, because that will be easier to explain. So 486, as I shall, there is one concept which is called as superscalar, which I will introduce in few slides to come. Meaning that what is what is a scalar processor? A scalar processor has got only one execution unit, one ALU, or whereas a superscalar has more than one. Meaning that in case of in the simplest form, let's say both processors are running at the same frequency, 486 running at 500 megahertz and Pentium running at 500 megahertz. Then in case of 486, it will take one instruction and it will, that pipeline, it will keep going inside, fetch, decode, execute, write back one after another. You can assume this as an assembly line of a car, that a chassis is put and the car rolls out after let's say half an hour. And on that assembly line, at any given point in time, there are 50 cars in various stages of production, and they just keep going on, going on. In our case, there are only 4 cars in 4 stages of manufacture, let's say. So point I'm trying to make is, now, as what is a superscalar? Superscalar is, this is Pentium. I'm sorry, this is 486, one assembly line with fetch, decode, execute, and write back. Okay. In case of Pentium, what happens is the execute. When it comes to execute, there are 2 execution units. So in simple form, you can say that all instructions at odd numbered instructions will go to one execution unit, or all even numbered instructions will go to the the adjoining execution unit. This looks simple because we will assume that there are no dependencies between these 2 instructions. Uh, so if you take that as an simple case, that all the instructions are are, let's say, one instruct certain set of instructions are incrementing one register, another set of instructions are running incrementing another register, so that there is no dependency between these odd and even. If you take this as an idealistic case, then this program running on 486 will execute one instruction at a time, whereas on a Pentium, which is a superscalar unit with 2 execution unit, will be able to execute 2 instructions in at the same time. So the program is same, but the microarchitecture is different. The implementation is different. Hence, in certain circumstances, the efficiency of Pentium is more than that of 486. Does this example help you understand the concept?
Yes, sir. Yes, sir. Actually, that example of horizontal scaling, that 2 execution cycles. Yes,
Yeah,
actually, it helps. Yes.
yeah.
Mm,
Okay.
I doubt it's clear, sir.
Thank you, Rahul. Uh,
After that,
Pavitra, you
Mayank
can
has a question.
give chance. Mayank, yeah. Mayank, go ahead. Unmute yourself.
Hello, am I
Yeah,
audible?
Mayank, I can hear you.
Yes, sir. Sorry, sir. This question is just off the track. So, as we are just decreasing our transistor size, so we know that Moore's law will be vanished. Like
Yes.
if we say we can't decrease our transistor size of transistor, like we will be stuck at that position.
Yeah.
So the first question is this statement correct that we will get stuck? Or if it's so, then what should we do?
Okay. So, uh, to answer your question, uh, that currently the state of art feature size. So, what is definition of feature size? Definition of feature size is what is the smallest or the rather the thinnest line you can draw on a silicon. Okay. So once upon a time, 100 nanometer was state of art, maybe 10 years ago. So the smallest line we could draw was 100 nanometer. That kept decreasing, decreasing. And today we have silicon available which conforms to what is called as 3 nanometer. Okay. And people are
Yes.
again trying to go further down and down. And but as you rightly said, there is something called as a limit. Maybe you cannot draw a line which is thinner than one atom, as they say. So there will be some limit. So let's not uh, think about what is that limit, but that limit is definitely going to be there. Okay. So now what happens is once that limit is reached, you cannot pack more and more transistors on one silicon. Okay, so there is a limit to that. And as a result, the number of transistors will get decided. As a result, the logic that you can put will get decided. So you will have that kind of limit as to reach that, okay, we cannot go beyond this. So a chip is having so many transistor, and this is the this is the functional units and all those things, microarchitecture that we have been able to fit into that. Okay. So now, once that physical limitation is reached and you have physical chip inside which certain so many billions of transistors have been packed and they give certain functionality, the next step that you do is, which I shall also describe in this slides to come, is that you put two of them. Okay. So like you must have heard about multi-core processors. They already are there. That is because
Yes, sir.
what is that, on one silicon piece of silicon, whatever is the maximum size you can have, a reasonable size you can have, we have certain number of transistors you have put for a given feature size. But we want more. So what do we do is you put two of them and we link it when we link it through a memory caches. Some of that I will cover today, and more of that I will cover next week. So as a statement was made earlier, horizontal scaling. So you cannot go deeper. So you go wider in the sense that you put more and more such chips, and then you link them up. So how you link them up, I will some of the methods I will let you know today, and some of them next Monday. Okay. So that is
Okay, sir.
answer
But
to your
that's
first question.
yes, sir.
What is the next question?
Adi,
So,
would you like to
like,
answer
No, no,
something?
Mayank said first question,
Okay,
which
okay,
means he
okay.
has one more question.
Yeah, fine, fine.
yes, no,
Please.
sir, no, sir. This is the question, sir. So we will be doing the performance on the basis of area, right? We will be increasing area to get the performance.
Area meaning, see, there
But
is a area of the silicon also is limited in the sense that how much can one wafer hold? I mean, how big can one wafer be? There is a physical limitation to that as well. So what we do is, so when the wafer reaches its limit, we can put multiple such wafers next to each other in one package, one chip, one physical chip that you see. Okay, once that
yes.
limit is reached, we put more such chips next to each other. When that limit is reached, we put more such motherboards next to each other. I will tell more about it in the next on next Monday. Okay.
Okay, sir. I was thinking like, can we change the if we have one chip produced, can we change the whole chip to within that number of transistor and that area? Can we produce more performance, like changing some architecture or changing the ISA or something like that?
No, see that functional changes, functional improvements one can definitely do. And those are independent of the feature size, right? That anyway you can do. One of the things that, one of the impediments that come in is that once a ISA has been decided, then defining a new ISA becomes a problem because there is no compatibility. And that's the reason why Intel is still continuing with, though they have made it 64-bit, but the ISA still remains same. What they call it now, they call it as 64-bit EM64T, but the original instruction set or the original memory model, all that remains same because investment in software is more costly than investment in hardware. Hardware you anyway are going to throw after 3 years or 4 years. But software, what you have bought, you don't want to invest one more lakh rupees in buying a new AutoCAD. You will say that I want to use the same license over the next hardware that I buy. So the more efficiency can come if the ISA is defined differently, but then the compatibility is lost. So there is always a problem with that. So that is what is more detrimental than anything else.
Okay, sir. Okay.
But the efficiency can definitely improve by defining new functionality or doing the things in a different way inside the CPU. So that's why that boundary line is important, that at the boundary of the chip, the instructions that will enter the chip, they are fixed. I mean, that you are not going to change the way they are. Those
Yes.
set is not going to change. Okay.
Okay. Okay. Okay. Yes.
So Adi, does that answer your question as well?
Yeah, I think my question is answered. Just I mean, yeah, it's a historical question. Uh, have you seen processors which are capable of executing something known as a dynamic ISA? I mean, one example can be FPGA, right? You can configure an FPGA to expose a different ISA on the fly. But does the concept of a dynamic ISA make sense? Because if you have dynamic ISA, then what it does is that it improves your efficiency on the fly without needing to design anything else, right? It is a truly a single architecture for any sort of application. I don't know. Okay, yeah, your call.
Yeah. So yes, as you rightly said, there are what is called as reconfigurable processors. Okay, but uh, describing them to this audience may take time and may be beyond the scope of the school. But to answer your question, uh, yes, it has to be FPGA based because then you want to dynamically reconfigure it. However, having said that, that reconfiguration may take some time penalty in some sense, but and what I would rather say is that in this the concept that you are proposing is definitely workable and people have used it. And what happens is the your hardware remains same in the sense that you have a motherboard or a box, that hardware remains same, but it reconfigures itself to suit the workload. For example, suppose you are running a scientific program which does a lot of floating point calculations, then you would like the same piece of hardware that you have be efficient to floating point operations, and you can reconfigure it in that way. And suppose subsequently you want to use it for, let's say, AI workload where a single precision integer is good enough, then but you want more such in parallel, then the same set of transistors or gates or basic what they called as configurable logic blocks. Those blocks are configured with a new bit file, as they call it. So the bit file is a way by which you change the functionality of the field programmable gate array. So that can be changed. So that is very much possible. So the concept that you have said is in use, but again, more research needs to be done to make it more acceptable or to bring it in mainstream. Currently, it is being used in some pockets of research or for specific purposes. Okay, thank you, Adi. I think Prachi, you
Thank you.
can take the next question.
Yes, sir. No questions for now. No more
Okay,
questions.
okay,
Yeah.
good. So I will continue from where I left. So we had seen this a basic thing where we had a layered architecture starting from transistor. We then have logic gates. Then we have basic functional units. The functional units are put together to form execution unit. A collection of execution units with a control unit forms your microarchitecture, which is capable of executing a sequence of instructions. And apart from the instruction, the instruction set architecture also defines number of registers, how the memory is accessed, supported data types, and you can run a simple program on this, or you can run an operating system, and through the operating system, you can run an application program. Okay. So let's move ahead. So the we will just in the morning it was referred to us that you write a program in a higher level language, and then you use a compiler. The same concept I am trying to now expand. So you write a higher level language program let's say a is equal to a plus b plus 1. So new value of a is equal to old value of a and value of b, which is, and the sum is incremented by 1. But the CPU does not understand that. It understands only machine language, or which has a 1:1 association with the assembly language. So that's why the higher level language has to be, statements in them have to be converted to assembly language. As I mentioned in the morning, that you have an operand and an opcode. So that is done by the system software tool like a compiler. Okay? Then whereas the assembly language program is nothing but a sequence of instructions. So, and those instructions are part of the instruction set architecture that we saw some time ago. So this it would be like this. In this case, you will the instruction would be that add a comma b and increment a. So in this, each instruction has an opcode which is onto onto the left, and each has an operand which is onto the right. So in this case, in the first instruction, add is the opcode, a and b, which are the registers. They are the operands. And in the second case, a is the operand. So in the morning, I had said that there are some operators which need two operands, some operators that need a single operand, depending upon what operation you wish to perform. So the opcode, as I mentioned, specifies the operation to be performed, like add, increment, whereas the opcode, it specifies the where the data is located. So now in this case, both the operands are located in the register, but in some cases it may be located in the memory as well. So that depends upon the instruction set architecture, what capabilities that instruction set architecture offers. So this is how uh, the whole flow is, that you start off with as a user, you start off with statements in higher level language, and you write a few of them. You form a construct, you form a structure of them, like you have an hierarchical program which has got a main program, and there are some subroutines, and you design your flow chart and convert that into a program. But finally what it boils down to is that you have at the instruction set architecture level, the processor will execute a sequence of instruction like what is shown here. So now let's now deep dive into the processor. So there, this is one of the execution units that you have, arithmetic logic unit. So as the name suggests, it can perform arithmetic operations and it can also perform logic operations. And we saw a glimpse of that, that this ALU is actually controlled by a control unit, which tells it that, oh, this is the instruction that you should be executing, and these are the operands. So this is how it gets. There is one path through which the control path through which the instructions enter, and the other path the corresponding data enters. So here, so corresponding to this first instruction, there is a corresponding operand. Corresponding to this fifth instruction, there is a fifth set of operands. So like this, they keep one after another instruction, and the corresponding data keeps entering the ALU. The ALU takes action on those instructions. Okay? And then it produces the result. So every instruction operates on its own data, and it produces the result. So that is the thing which we saw: fetch, decode, execute, write back. So that's what is happening. So this is typically that happens in the combination of control unit and the ALU. So, so this data that comes here is in blue, in light blue in color. That's two operands, 2 and 2, and the instruction that you say is add, and the result that you get, which is in green, that is 4. So this is one example by which instruction entered the ALU, its corresponding operands entered the ALU, and then a result was produced. Moving ahead. So where does this come from? So this data and the instructions, they come from a memory, some kind of memory that should be there. That is where it comes from. So this typically looks like a one Neumann architecture where there is a unified instruction and data. However, if you draw a line in between and separate them out, then it will become a Harvard architecture where data will come from an independent memory and instructions will come from an independent memory. So this is a source that it's some storage in some form is there from where the stream of instructions and the corresponding stream of data keep entering the ALU, and once they enter, obviously the result has to be produced and it will again go back. That's the write back stage. So instruction fetch, that along with that instruction the data comes in, then you decode the instruction, what that instruction says, then execute it, produce results, and results go back. So that is same as what we discussed earlier in terms of the cycle that von Neumann suggested. So now there is a concept of register. So the concept is same, that you have a main memory which has instruction data, the instruction is coming in. However, in the path of data, you have registers. So now why do we need this register? The reason is very simple, because you can see that now you see here a boundary which is a CPU, and we had said that the CPU is separated out from the memory. So in this case, this is the boundary of the CPU, and getting anything outside the boundary can be slightly time consuming. But if you have something at your hand very close to the ALU, physically also very close to the ALU, then a small set of the actual data, which is whose owner is the memory, part of that is stored in registers. So registers can directly feed the ALU. So that is the significance of a register. And frequently needed data is typically stored in the register. So now the compiler or the or that entity that generates the program automatically takes care of this. However, in you, some of you who have done advanced C programming would know that there is a keyword called register, which you can attach to a variable, by virtue of which that variable will be maintained in the register. The potential candidates for being in register, suppose you have a loop for I equal to 1 to 100, then I is a potential candidate to be in register. So you can, as a user, you can programmer, you can specify that, and many times compilers are intelligent enough to detect such things and take advantage of the fact that this is like a use and throw kind of a variable, that at the beginning of the loop you initialize it, and after the loop is over I loses its significance because that is no longer required. So these are the potentials. There will, you'll find many such example where you have a potential candidate to variables which will reside in the register. So that is the next thing that CPU designers do, that they design include registers inside the CPU in order to make things fast enough. Okay. So of course the result will also go back to the register. So in the example that I gave you, add A comma B, what happens is B is added to A. So both A and B are presented to the ALU. The result goes back in A. So that is how the register instruction set architecture defines the function of add A comma B. Now, why this another green line here? Because registers are limited. So at some point in time, to reuse the register, you may have to vacate them. And some of the used registers, remember, the ownership of the data is in the memory. Every variable is identified by where it is stored in the data memory. But it is brought into the register for temporary use. And if that register is required to be used for some other purpose because of the limited number of registers being present in the CPU, it may be required to put it back because you want to bring in a new data which is going to be used more frequently now onwards. So once that are not being used, they are vacated, and if they are not written back here, they may get overwritten. So that is that it's a part of the assembly language program that you write, that or the compiler does that for you, that the updated data in the register is written back to the data memory so that it can be used later. Yeah, so to explain what I said, the CPU executes instruction one after other in a sequential manner. I've already told that. Each instruction has its respective data or corresponding data. And now we have to go through a cycle. Okay, so now you might have seen that in many cases where such a thing happens in real life, that you have to do things in a cyclic manner. Then you have a motor driven something, so that there is a wheel which moves, and with that corresponding to, or if you uh, uh, might have seen a steam engine or any such mechanism, mechanical mechanism, where there is what is called as a prime mover. So that prime mover is typically a motor, and that motor, when it moves, it certain things happen in synchronization with the movement of the motor. So this, in case of CPU, to make this happen, that fetch, decode, execute, write back, fetch, decode, execute, write back, you need to happen at a in accordance with something which is called as a clock signal. Okay. So a clock signal is typically depicted like this. Over a period of time, it will keep pulsing. So it's like a heartbeat goes up, the signal oscillates between logic level 1 and 0 at a periodicity, at a regular periodicity. And that period is like on a scale of time. So if this time period is 1 second, then we will say that the frequency of this clock is 1 hertz. Or if this period is 1 microsecond, so 1 upon 1 microsecond is 1 into 10 raised to 6 oscillations in a second, which makes it 1 megahertz. So typically 1 megahertz, 1 gigahertz, these are the frequencies at which the CPUs are run, and they decide how fast the CPU is going to run. That is, suppose you have two processors, one with, let's say, period of, or a CPU with a clock running at 1 gigahertz and another one running at 2 gigahertz, then the uh, second processor is going to run twice as fast as first, because internally everything is happening at twice the rate of the first processor. So the clock is an important attribute and contributes to the performance of any CPU. So that was a snapshot. In the previous diagram, we had shown a snapshot of what the important things in the processor are, because we were trying to zoom out. So now if you zoom out further, you will find that these are some of the entities that are present inside any CPU. What remains same, what we saw earlier, was the main memory, which is divided into data and instruction. The ALU, where all the action happens. The output, which were not shown earlier, it goes into accumulator, and from there it goes to register. The source operands also come from register. So that is the data path. But this, where do this register get data from? They get it from the data memory. And how do we get data from the data memory? For that, you need to provide the address. So there is a memory address register. So data memory address register, which provides the address. As a result, the memory gives back the data which is held in the temporary registers called memory data register. From there, it will come to the uh, general purpose register, because the ALUs can take operands which are coming from the register. So though all the operands you want to operate on are in the memory, initially using a load store kind of unit, they are brought in from the memory onto the register. From register, they are used, and the data result is again written back to the register. Now, what operation should be performed on the ALU in every cycle? That is told by the instruction. And where does instruction come from? It comes from the program memory. So how do you fetch the instruction? You have to provide the address. And who provides the address? Address is provided by program counter. There is an entity called as program counter. Uh, and some of you may be aware that there is a concept called as reset, power on reset. or resetting the CPU, at that time, typically the program counter would be initialized to 0. So at location 0, the first instruction is written. So 0 goes to the memory, it returns with an instruction. That instruction contains two parts, the opcode and the operand. So let's say the instruction is add a comma b. So it will be temporarily brought in into the register. Then it will go to the decoder. The decoder will separate out the operand, the separate out the opcode. So that opcode will say that it's an add. So the control unit will tell the ALU, you need to add, you have to perform an add operation. But then what should it add? That is told by the operand. Suppose the operands are a and b. So if the instruction is add a comma b, then a and B. So there are register A, B, C, D, E, F, G, H here. So out of which A and B are selected. They are presented as two inputs to the ALU, and the ALU generates an result, which in this example goes to an accumulator, and from accumulator it goes back to the source register. Thus, one instruction is completed. Now, once this instruction is fetched and it reaches its end of life, the program counter is incremented by 1 and the next instruction comes. An instruction could be jump. Let's say you started with 100, 101, 102, 103. They kept coming in and you are doing add a comma b, c comma d and all that. An instruction comes here, jump 200. So the program should now from 105 should go to 200. How will it do that? The control unit, though the path is not shown, will push 200 in the program counter. As a result, what will happen is next clock tick comes, 200 will be presented to the memory. The instruction at 200 will be brought in and that would be decoded. Then 201, 202, like this, it will go on. So the essential concept remains same: fetch, decode, execute, fetch, decode, execute. And for that, the program has to. Now in this case, you will see that there is a separate path for program and separate path for data. So this resembles more of a Harvard architecture. But had it been one human architecture, then there would have been a multiplexer that merges both the paths into one appropriately, so that externally from the CPU there is only one address bus and only one data bus. In this case, this address bus here is for program memory. This address bus is for data memory. This data bus is for program memory, and this data bus is for data memory. You would also notice here that the data bus actually carries the instruction here, and it is pointing, this arrow is pointing towards the instruction register. Whereas this pointer is bidirectional, mean if it's a memory write cycle, data will go from memory data register to the memory. If it's a read cycle, data will come from the data memory to the memory data register. Okay. So to elaborate further, as we already know, I have said this multiple times. These are the tasks that are involved: fetch, decode, execute, and write back. These are the 4 tasks that typically keeps happening in a cyclic loop. Okay. So this is what I wanted to cover in the first hour. We had a little bit of spillover. Doesn't matter. I will cover up in the subsequent uh, uh, classes. Okay. So the next topic for us is to know that we have now understood the basic thing. So any questions about this, the basic way in which it happens? So the take home, the summary is that you have the separation of execution unit and control unit together from the program memory, and then fetch, decode, execute, write back are the cycles that are followed. And there is a clock which keeps ticking and makes the control unit go through these phases, and one after other they are done. And the program is a collection of a set of such instructions which are executed typically in these four states. That is, it goes through first fetch, then decode, then execute, and the results are written back. So if anybody has any question, you can raise hand, and Prachi will allow you to speak. All right, looks like there aren't any questions, so we will move over to the next topic, where now that we understood how the basic thing works, how the uh, what is the life cycle of one instruction, and how a sequence of instructions come in one after another, let us see how we can make this efficient. So first we will look at the single CPU systems. Okay, so we will, because later we will look at the multiprocessor systems. So first thing is that even if you use multiprocessor system, there is always an attempt to improve the performance of a single CPU. Because if this performance of a single CPU is improved, that gets multiplied when you use multi-CPU system. So single CPU system has these mechanisms. I will explain each one of them. One is ALU width. I will explain what it is. Then the frequency. We will making use of pipelining. I will explain what pipelining is. Then what is superscalar, and advanced instruction, and finally multi-core. So all this you do, there will be a limitation in the performance, and as I was mentioning in one of the answers, that that's where parallel computing overcomes this limitation, because then you can put more number of such improved cores. Each one of them is a single CPU. So that we will cover in the next week, about how parallel computing helps us. But today we will be concentrating on the performance improvement in a single CPU. So ALU width. All of you know that 8085 is an 8-bit processor, or 80386 is a 32-bit processor. So what does this bit means? It means the number of bits that the ALU can crunch at a time in one clock or whatever. So like if you want to add two numbers, 8085 will be able to add two 8-bit numbers. 80286 will be able to add two 16-bit integers, whereas 386 or ARM V7, which is a 32-bit processor, can add 32 bits or 4 bytes. But the newer Intel processor and the newer ARM processor, they can operate on 64 bits at a time. So basically it is a width of the ALU that matters, and the adder, etc., which are present inside the ALU, they are capable of crunching as many number of bits as is mentioned in the specification of that processor. Some of the examples of them are written here. Okay, so that is like a 16-bit processor is faster than 8-bit in doing its work, because of the width has increased. So the next characteristic that can be tweaked is clock frequency. So to give an example, when 8086, rather 8088, which was used in the first IBM PC, which was released in 1981, was running at 4.77 megahertz. So that's an awfully slow kind of thing, because today we are used to gigahertz frequencies. We hear about 2 gigahertz, 2.4 gigahertz, 2.9 gigahertz. So those CPUs are 1,000 times faster, almost 1,000 times faster than a old processor running at 4.77 megahertz, because the speed has increased three orders. Like what was megahertz has become now gigahertz. So it's obvious that the programs are going to run faster. But one should remember that if you keep increasing the frequency, it is bound to increase the power consumption. Why? The reason is very simple. A transistor draws current when it switches state. Otherwise, it takes what is called as quiescent current. So that is very, very low, maybe in microamperes or something like that. So if there is no clock which is present, then the CPU is going to consume very little energy. As the clock speed increases, the power increases is proportional to square of the frequency. Okay, so that is very important. Like you double the clock frequency, your power consumption will become fourfold. Okay? So as a result, more heat needs to be dissipated. So you must have seen those tall heat sink with fan on inside motherboard. They are used to extract the heat, to dissipate the heat which is generated inside the processor. Okay, so that puts a limit on what could be the frequency. So this is called as a frequency wall. So you might have noticed, in case you are following, uh, maybe about 10 years ago, Intel started with 1 gigahertz, 2, 2.3, 2.4, 3, 3.4, but they did not have 4 gigahertz processor. Why? If that was the case, then a normal method using a fan and a heatsink will not be useful to remove the heat that can come if the frequency is increased to beyond a certain limit. So this frequency is a important issue, and there is an upper limit to which a CPU would be safely be able to run. So that's why these days you have found that most of the CPUs, they typically run at 2 or 2.5 gigahertz, though in theory we have definitely reached 3.5 gigahertz or close to 4, but the heat that is dissipated, that becomes a big bottleneck. Okay, so you have to limit the frequency so as to stay in a safe range of operation. Now there are other things that also decide what is going to be the clock frequency, like feature size. So those are the thumb rules, and the foundry which is developing the chip will give an indication as to what feature size it can support. So what kind of clock frequency it will support, so that the CPU can operate in a safe zone and not get into a thermal runaway due to increased clock frequency leading to the increase in power. So what are the improvements in the clock frequency that you can do? Let's try and see. So the clock is what is the rate at which the ALU also operates. So this diagram we have seen earlier, we only added a clock to it. So to explain it, let us take a CPU which is operating at a frequency of 1 megahertz. Okay, so when it is operating at 1 megahertz, the period is 1 microsecond. Okay, so this is how there is a relationship uh, between between the frequency and the period. Okay, so now let's take another clock V, which is faster. Why is it faster? Because if you notice here, it is operating at the double the frequency. Hence, the period has become half. So you will see that in a given time, let's say if you take a given time of 2 microseconds, you have 2 clocks for A and 4 clocks for B, which means increasing the clock frequency reduces the time period, and the work that was, let's say, suppose a work takes 100 cycles, then this will take 100 microseconds A, but B will take only 50 microseconds. Because what we are counting, what is the basis for our counting of the work? The basis for counting of our work is in terms of how many clocks are required. How many clocks? Because everything is happening at the rising edge of the clock. Some action has to happen. It is happening at the rising edge of the clock. Okay, so increasing the clock frequency results in reducing in its period. Thus, the work is completed faster. Okay. And if it's 4 megahertz, then you will see that further this gives you an idea as to the work will be done in 1/4 the time as compared to A when C is used. So that is how the improvement in the clock frequency results in lower time period and increase in the throughput over a given period of time. Okay, so what we are doing is I will explain the concept of pipelining in the next slide. So we in that, because of pipelining, we are able to execute the instruction faster. I will explain that in the next slide. I think this sentence has come wrongly here. Okay, so I'll explain pipelining here. Okay, so now what we are doing, let's try and understand how the pipelining helps us in improving the throughput of a processor. So first thing to be noted, an instruction goes through 4 stages of execution. First it is fetched, then it is decoded, then it is executed, and it is written back. So if you take it on a scale of time, then you will find that in first clock T1, instruction 1 is fetched, decoded, executed, and then written back. So what is happening is that we are able to finish a instruction in 4 clocks. Now, if there was no pipelining, then what would have happened? In that case, fetch of next instruction would have begun here, okay, in the clock number 5. However, what we have done is we have, if you notice in the diagram that I showed you, fetch is done by the control unit. Decode is done by the next unit, which is instruction decoder. Execute is done by ALU, and write back is done by the load store unit. So these are independent activities, and if you take just one instruction, these 4 independent activities are done by 4 different units inside the CPU, and output of one unit goes as an input to the next unit, in the sense that the load unit will load the an instruction, it is fetched. Then the control unit will decode it. The ALU will execute it, and the load store unit will, another unit will write it back. So if these 4 independent units are doing 4 independent tasks, then once, if you notice here, this for instruction 1 in cycle 1, T1 in cycle 1, that is T1, the fetch unit was busy. In T2, T3, T4, it is not required by I1, because in T2 I1 needs decode unit, in T3 I1 needs fetch unit, execute unit, and in T4 it needs write back unit. So because fetch unit is free, in T2 what we do is we fetch I2, which means that when the decode unit is decoding I1, in the same clock we are using the fetch unit to fetch the next instruction, and you continue this in time period 3. The first instruction has gone for execution, so decode unit is free. So second instruction is now decoded, and because second instruction is decoded, and it has left fetch unit is now free to take instruction 3. So if you go by this logic, what is happening is every clock period a new instruction is entering the CPU. If there was no pipelining, after 4 clock periods, the second instruction would have entered the CPU, and it would have gone through one unit 1 clock at a time. So 2 instructions would have taken 8 cycles. But here, if you notice here, since every clock an instruction is entering, after a delay of 3 clocks, the first instruction is completing. In the next clock, the next I2 is completing. In the next clock, I3 is completing. In the next clock, I4 is completing. So what is the effect that we are getting here? The effect we are getting here is, for the first 3 clocks, no instruction has finished. When has the first instruction finished? It has finished only in the 4th clock period. However, in 5th, 6th, 7th, one instruction is getting completed. So how can we interpret this? We can interpret it as this in this following manner. For first 3 clocks, no instruction is completed. But after a delay of 3 clocks, every clock period, one instruction is getting completed. See, there is a W in every clock period. So what are we doing? By overlapping the activities of fetch, decode, execute, and write, effectively, we are executing one instruction per clock. So this is the beauty of pipelining. Okay. But what can happen is, if this is okay, if I1 is at 100, I2 is at 101, I3 is at 102, I4 is at 103, like this sequentially, if the instructions are in the memory, this will work. But what happens, as I mentioned to earlier, I3, if I3 instruction is jump 200, that means this instruction I4, which has come from 103, it is not to be used, but it has entered. That means you have to discard it and you have to execute the instruction starting from 200. If such a thing happens, then that is called as a control hazard. Why does the control hazard come? Because of branch. I gave you an example. The instruction flows from 100, 101, 102. Next should be 200. Why? Because I3 is jump 200. So anything that changes the program counter. Can anybody tell me, like, jump is an instruction which changes the program counter? Do you know of who has studied assembly language programming? Can anybody unmute yourself and tell me which is another instruction that can change the program counter?
Exit or break.
That is at a higher level. You are right. But have you studied assembly language programming by any chance?
Yes, sir, I've studied, but I just don't remember at this moment.
Have you heard about this instruction call? Call a subroutine?
Call, yes, sir.
Okay.
Yes, yes,
So,
yes.
like jump, call also changes. Similarly, like jump is an unconditional. So there is a jump on no zero, jump on zero. You must have heard about them, right? So uh, one is unconditional jump. There is a conditional jump or a conditional branch. Third is a call, calling a subroutine. So does anybody know another variety of instruction that also changes the program counter? Like 3 types I have mentioned. Those who know assembly language programming. Okay, the answer, the clue is call instruction. Can anybody tell which instruction corresponding to call can also change the program counter when executed? Okay,
Hello,
the
sir.
address. Pardon?
Sir, I haven't studied assembly programming.
No, that is fine. That is fine.
Like
That's why I
call,
said.
so maybe while changing the context, while calling one function or something like that, the program counter may get changed.
Right.
Like
So
if,
sorry, the answer that I was looking for is return. So call has a corresponding call as return. So I think you are trying to mean the same thing, that the context changes because you come back to the main program. Okay. So typically in the main program, you call a subroutine with some parameters, like you have function call in C. Same thing in assembly is there is a subroutine call, and call is an instruction. Similarly, return is another instruction, that is return or put at the end of a subroutine. So it comes back to where the call was made from. Okay. So I hope you all have understood this concept of pipelining. So here it compares the uh, the non-pipelined. If you notice here, every instruction takes 4 clocks. So one instruction completes, then another instruction comes in, then third, fourth. So 4 instruction, 16 clocks, 4 into 4. Whereas here it is initial delay of 3 clocks, then every instruction per clock. So 4 plus 3, 7. So there is a parallelism, as many number of stages. So now in this simplest example, there are 4, but in real life, you can have like 5-stage pipeline, 7-stage pipeline, 12-stage pipeline, 20-stage. So depending upon how complex the processor is, you have a number of stages in a pipeline. Okay. So I hope that explains how this is one architectural feature that improves your execution. Now remember, the programmer has nothing to do with this. Programmer has only written a sequence of instruction, but this is an architectural improvement, and believe me, from 8085 onwards, this feature has there in every processor that is available in the market. Okay. So now coming to another concept, I had mentioned to you scalar versus superscalar. So this scalar versus superscalar is
Sir, sorry to interrupt, sir. Sir, how much content for this session is remaining, sir?
yeah, I will finish off after this superscalar approach.
All right, sir. Okay, sir.
So in superscalar approach, if you notice here, in a scalar approach, only one green block will be there. Okay, just one green block. Okay. Which means only one execution unit. So this pipeline, fetch, decode, execute, and write back. So only one pipeline like this. In case of superscalar, the instructions are still sequential, but what does the decode issue unit do or the fetch unit do? It takes more than one instruction at a time. Like if you have 3 execution unit, 3 instructions will be fetched at a time. I am not going to describe here the dependencies and other thing, but you can assume that if all instructions are independent of each other, they can be given to multiple execution units. So that is a superscalar approach. So 486 was a scalar processor. Pentium was a superscalar. So again, remember, no change in the program. Program is exactly same. You are only improving certain features inside the processor so that it can do things faster. So this is a micro architectural improvement. And remember this golden rule, that any feature you add for improving the performance, it can never ever be at the expense of accuracy. Accuracy can never be compromised. So any feature that hardware engineer adds, he makes sure that the program will run as accurately as they were executing before. So this is very important. Like, to give an example, suppose I design a new car and add so many features. I will say that it is in the same price. I'm giving you so many features. So speed goes so high. The rate acceleration is so good. Everything is good. But I tell you that sometimes the brakes may not work, because that's a compromise I have made, because I am concentrating only on performance. Nobody will buy such car, because the life of a person may be at driver may be at stake, or the passengers may be at stake. So any improvement you do, you will always make sure that its performance, whatever accuracy you have, that accuracy is maintained. Like in no circumstances will the CPU perform and produce wrong results. So this is always kept in mind, that accuracy is always maintained. Okay, so this is how it works, the superscalar. So it's anyway a pipeline unit is there, but the next improvement that you do is you put 2 pipeline unit next to each other, so that the execution happens. Like it's possible that you can have 2 instructions being executed in parallel. So that, because there are 2 executions, remember in the previous diagram, I had shown that the register file is same. The fetch unit, the memory, everything is same. Decode unit is same. Everything is same. What is improved? The improvement is in number of parallel execution units. Why we could do this? Because transistor budget increased from 486 to Pentium. So how do we put it to good use? By adding more execution unit. So here I will stop. I guess it's 12:30. So we had 1 hour of session, and if there are any questions, I will take it now.
Excuse me, sir.
Yeah, please.
Sir, as you said that there will be only one fetch unit and decode unit, but as there are multiple execution unit, so we do so load fetch unit and decode unit will be doing everything once at a time, once in a clock cycle, right?
But what they will do is they will fetch 2 instructions from the memory. Are you getting me?
Sir,
See,
can you go
imagine,
previous
imagine,
slide?
imagine it like this. Okay, there is a box, and there is a box has a set of papers in it, and your hand is going inside and pulling one paper at a time. This is a scalar unit. Okay, but now imagine that there is a in a superscalar unit in the box. What you have done is you have stapled 2 papers together. Okay, so when you are pulling out, how many papers are you getting? 2 papers. While issuing, what are you doing? You are pulling those papers apart. So you have 2 papers, 2 individual papers, one paper given to one person, another paper given to another person. Are you getting the similarity?
Yes, sir. So
Okay.
our memory is increased or the memory is
Width.
same, we are fetching two from it.
So your width, the path from memory
Okay,
to
sir.
that path is increased. So you are getting, or path is increased, or you can pull it faster. I mean, that depends upon the implementation. Like,
Okay, sir. In the same cycle, pull it two times, you're
yeah.
saying.
So like to give an example, the data path between memory and the CPU in 486 is 32-bit. In Pentium, it is 64-bit. But both of them are 32-bit processors. Okay.
Okay. Okay, sir.
Anybody else has a question?
Sir, what if both the execution units are concurrently working as they are seeming to work?
Yeah.
And what if they are working on a same register? They are applying the changes on the same register, so they might be overwriting each other's changes
Correct.
there.
Correct. Exactly. So I had made this statement when I said that you can give odd instructions to one and even instruction to another. I had made this statement that they are independent instruction. However, there are what is called as data dependency, and there is what is called as control dependency. So what you are explaining is a data dependency. Okay. So now there are these are hazards. These are hazards in the sense that you cannot issue. So what, there are 2 ways of handling this. The 2 ways of handling this is the issue unit takes a decision whether 2 instructions can be issued to 2 units in a given clock. I mean, if it's the case like you have explained, it will not be able to, because remember that golden statement, accuracy cannot be compromised for improvement in performance, right?
Yes.
So it will not issue. That is one option. Now there are ways of overcoming this. Uh, since this is beyond the scope of this school, I will not be able to do it, but you can look for there are something called as false data dependencies. There are something called as true data dependencies, and there are something called as false data dependencies. And for false data dependencies, there is a method called as register renaming. Okay, so if you take any standard book on computer architecture, it will have these concepts explained. So you are right that you cannot issue such instructions, but to issue such instructions, there are some workarounds, and that has to be implemented inside the architecture. Okay.
Yes, sir. Okay.
Okay. So
Sir, I
like
want to
data.
ask one thing.
Yeah, go ahead. Go
Yes,
ahead.
yes.
Please ask.
So I was just asking that you just explained that we can staple 2 pages and we can take out the pages from the box. But in reality, we have a single bus only. So how do we fetch 2 instructions at a time? So I just want to know this.
Yeah, there are 2 ways of doing it. One is that you operate that bus at a twice the clock rate, meaning within the period that you are fetching, you do it twice the faster. That is one way of doing it. See that you operate that bus at a faster pace. Other option which is commonly followed is you have the width twice. That means memory to CPU connection if the CPU is 32-bit, that connection will be 64-bit. You must have seen this thing inside a CPU memory module. Have you seen that? There is a small PCB on which multiple chips are there. Have you seen that? There
Yes,
is a,
sir.
if you
With
open
this
the
case.
PC, there is a connector, and in that there is a memory module. So now if each memory can give 8 bits, there are actually 8 such chips. So together they give 64 bits, right? So the memory is arranged as a 64-bit wide, though the CPU needs 32 bits at a time. Okay, so that is the way it is done.
Okay, sir. So, sir,
Did you
which
get
is
it?
the most, yes, sir, I got that, but I was asking, sir, which is the most efficient way, either to increase the bus, the size of the bus, or fetch the instruction twice in a cycle?
So both are used. Actually, that depends. Like if you are looking at the specifications of the memory module, they will give what is called as bandwidth figure. How many bytes, how many megabytes in a second. Okay. So that increase is done by both methods. Clock. So other thing, I don't want to get into those details. What they also do is one of the things that they do is they fetch it on both edges of the clock. So in the diagram that I showed you here, if you notice here, there is an arrow here. Can you see this arrow? And there is an arrow here, which is on the positive edge of the clock. The arrow is shown. Okay, here it will be easier. A positive edge of the clock and the positive edge of the clock. But some technique they use, they fetch the data in high going edge as well as low going edge. So twice in a clock period. So there are various ways that the hardware designers do it. What is important for us to note is the bandwidth is doubled. Okay, effectively the bandwidth is doubled. And sometimes what they do is, what I've not shown here is, there is an cache inside the CPU, instruction cache and data cache. So they will operate at a very high speed, and outside from there they will get the data. So I will explain a little bit of that in the second half. Okay.